next speaker is Maxwell Ramstead. He's a Chief Science Officer at Phenomenology Labs and an honorary research fellow at the Queen Square Institute of Neurology, University College London. And he has and still works very closely with Carl Friston. His research focuses on the free energy principle, Bayesian mechanics, multiscale active inference, and you already know it, computational phenomenology. And we'll hear a presentation about that today. So Maxwell, the floor is yours.
Well, thank you very much for the invitation. It's really great to see some familiar faces and to meet those of you that I don't know already. My talk today is titled A Gentle Introduction to Computational Neurophenomenology. Yeah, I'll jump straight to it. So basically what I want to do today is first introduce the notion of generative modeling, which has become very hot in computational neuroscience and other domains where we use computational simulations to study living systems, like computational biology. Then I'll talk about applying these methods directly to the modeling of first-person experience, which goes by the name computational phenomenology. And then I'll discuss possible extensions of this approach to the neural sphere. The sphere of bodily processes, connecting this up to the original neurophenomenological project proposed by Barela almost 30 years ago now. So what is generative modeling? Generative modeling is essentially a set of modeling techniques that have emerged in computational neuroscience. And the idea is always the same. We have some data, some observable outcomes that we can perceive directly, and we are trying to understand essentially the structure of the process that generated those data. In this family of techniques, these are known as hidden states or latent causes because they're not directly observable. I'll examine a few examples of this, and that will segue into computational phenomenology itself. One thing to note is that in this very simplified diagram that I've depicted here, causality flows in one direction, right? From the latent causes to the observable outcomes, their effects. Inference travels in the other direction. So as scientists, we generate data. And what we are trying to do in this context is to infer what are basically the things that caused the data that we're interested in, and what is the structure of the process, more specifically, that generated that data. In this context, the main mathematical tool that we use to determine which model is best is this quantity that I'm sure several of you have heard about, called variational free energy. Some presentations of this free energy stuff can be a bit esoteric. I think it's useful to just frame the free energy, this variational free energy in the context of statistics and generative modeling to kind of understand what it is. Free energy is basically the difference between the data that you expected under some hypothesis about how the data was generated and the data that you actually got. One thing to keep in mind in this setting is the difference between computational neuroscience and the computational theory of mind. And this is going to be an important distinction that will structure the rest of what I'm going to say. There is a huge difference between using computational methods to simulate biological systems as random dynamical systems, which is what we do in computational neuroscience, and making the metaphysical assumption that cognition is a form of computation. These things are not the same, and they often get conflated in discourse around computational neuroscience. So it's not the case that computational neuroscientists are committed to the computational theory of mind. So to consider an analogy, you can simulate the orbit of Jupiter around the sun using computational methods. So you're using computers to basically integrate your dynamical system that you're using to represent, Jupiter and its position in the solar system. You can do that without assuming that Jupiter's trajectory itself is in the business of actually computing an integral, right? These are very different. And so, yeah, what I'm going to be presenting is an approach from computational neuroscience. We're not assuming, just to be very clear, that the thing that we're simulating is itself a computation. These are a set of tools that we use to basically run the dynamical systems that we're interested in running. I just wanted to make that absolutely clear because it will be important in what follows. So the origin of these techniques is in neurophysiology, in techniques like dynamic causal modeling. As I'm sure all of you know, we don't measure brain activity for the most part directly using contemporary neuroscience tools. Usually we're dealing with a proxy signal, and we are inferring what must be the underlying neural activity that is generating that signal. So in the case of functional magnetic resonance imagery, what we're using is a bold signal, so a blood oxygenation level dependent signal. Basically, if you want to, and I'm sure, again, many of you already know this, but an fMRI is basically a gigantic magnet. And when you turn the magnet on, it interacts with magnetically active byproducts of cellular activity. So it's a proxy or an effect of the actual neurobiological activity that we're interested in. So what you do is you collect a bunch of this data, and then you have alternative models of what is the underlying connectivity structure that might have led to this data. And basically, you test a bunch of these different models using this variational free energy quantity. And effectively, what you're doing is saying, okay, well, under this model, I would expect this data, and I got this data. So what you do is you select the model that has the smallest divergence between the data that it predicts and the data that you actually get. And this is going to be a theme that repeats. So the context of invention of these methods, as I was saying, was dynamic causal modeling, statistical parametric mapping, and like the early days of fMRI in the late 90s and 2000s. So here we're assuming that there is a neurophysiological signal that we're collecting as a data, and we are inferring the unobservable underlying neurological activity that caused that data. A newer application of this is about like 15, 20 years old now, is called active inference. It's also known as computational phenotyping. And what it says is, okay, we're going to use the same setup here, but the data that we're interested in now is not this data that we're generating as scientists studying the brain. What we're going to do is consider the data that the body generates in its exploratory palpation of its milieu, its ecological niche. And then the model associated with this setup is not a model of the underlying neurophysiological activity, it's a model of the agent acting in the world. And yeah, so same idea, different domain of application. So computational phenomenology comes in when we ask the question, well, would it not be possible to take the phenomenological data that's generated on the one hand by classical phenomenological descriptions like Husserl's descriptions of time consciousness or object perception, perspectival perception, and all of this stuff, or qualitative, more applied phenomenological methods that you might get from like a structured interview methodology, for example. So would it not be possible to take this phenomenological data and to write down a model of the way that it is actually generated as sensation wells up in first-person experience? So here, the data that we're interested in is, as I said, this phenomenological data. And the model that we're interested in is the actual things in our life world that are generating this data. So the term computational phenomenology was first coined by Harland in 1984. And Harland was, exploiting some resonances between Husserl's formal descriptions of lived experience and, the possibility of formalizing that using a computational approach, kind of imposing an inferential reading on Husserl. And, in the interim, there's been a lot of work actually coming out of France and Jean Petitot's group on formalizing phenomenology. We see computational phenomenology as an extension of this. Sometime in 2021, Axel Constant and myself on the one hand, and Anil Seth on the other, we all kind of came to the same conclusion that actually these generative modeling techniques that we had used in the context of active inference could just be directly applied to modeling first-person experience. And so, that led to this initial paper where we describe the methodology in detail. Arguably, the first paper in this tradition was, at least in the modern rendition, is this paper on the bottom that we refer to here, Sanded Smith and et al., so a bunch of us, towards a computational phenomenology of mental action. We didn't necessarily realize at the time that this is what we were doing, but I would argue that's basically the first kind of use case of this methodology. This paper right here is basically a methodological manifesto for the approach, and recently we've published some more mathematically extensive treatments. So we said just now we're going to fit a model to the data that's being generated. We pick the model that makes the best predictions about the data, where the divergence between the predicted and the actual data is the smallest. What are these models exactly? These generative models. So generative models are widely used now. They're used in all sorts of areas of physics. This is where originally this comes from for us. But I mean, they're basically staples of machine learning at this point. And a generative model is just a joint probability distribution over all of the states that are relevant to your system to consider. And in this context, they're very useful because you can consider a generative model as basically a joint specification of hidden states, so configurations of states in the world, and the observable outcomes or data that you should expect under those configurations. Very schematically presented here. What I'm presenting basically is the Bayesian generative modeling approach in general and its application to computational phenomenology on the bottom. What you always have is some data. Then you have some beliefs about what is causing the data, some inferred cause. And then you have parametrizations of this relationship between what the causes and the consequence. In effect, you have some beliefs about the prior state of the world before you observe it, and you have beliefs about the way that the world generates data, which you might link up to sensory motor contingencies and this kind of thing that emerges in the more embodied inactive literature. In generative modeling, we usually assume that there's a true cause or ground truth. This is something that we don't have to assume in computational phenomenology when we are just modeling lived experience directly. So in computational phenomenology, the data becomes experience or our descriptions of experience. We are trying to understand the things in the life world that are causing those experiences, and we're basically deploying the same kind of statistical modeling techniques. In practice, these models get treated with a bunch of Greek letter complicated mathematics, but what these models essentially tell you is that your posterior beliefs so what you think is actually out there, what's causing the data, is generated by combining what you learn from your senses, what you learn from the data, with what you believed prior to sampling anything. So I'll skip through just the math here to get to the methodology. Standard methodology in computational phenomenology is to always start from a rigorous phenomenological description, like I was saying. So this can be like, a classical phenomenological text, like Pierre was discussing in his presentation. So you could go to Merleau-Ponty or Sartre or whoever is your favorite phenomenologist to get some descriptive materials. But you could also use, more contemporary interview techniques of the sort that several of you in this room are interested in. So starting with a phenomenological description, what we do is we first add an additional layer of formalization to that description, moving to a so-called state space formalization of the description. That makes it amenable to generative modeling. So based on that formalization of the description, we can write down a generative model of how essentially experience wells up in the first person. And then there's an optional move to look at how this description might constrain possible biological implementations. That's the move from computational phenomenology per se to computational neurophenomenology. So here's an example. You can look at the example in detail in this paper that's referenced at the bottom here, Towards a Computational Phenomenology of Mental Action. So Lars Sandved Smith, the first author, is an experienced meditator and meditation teacher. And he chose the phenomenological cycle of sustained attention in a focused attention type meditation as the target for formalization here. So this is in effect a phenomenological description of the cycle of sustained attention, where we begin and we're focused, then we get distracted, we become aware of the distraction, and then we redirect our attention back to a focused state. So Lars began by writing down this essentially description of his phenomenological experience, and then moved from there to a formalization of that description using state space techniques. So here he distinguished two states, the true state and the perceived state, and then re-describe the cycle of focused attention using those two states. So basically we begin in the focused state where our true state is focused and we also perceive that we are focused. Then in the distracted state, the perceived state is still focused, but it's a misperception. The true state has changed to distraction. When we become aware of the distraction, the true and perceived states realigned. Then there's an action is selected, a mental action is performed, and attention is redirected. So both states realign to focused. In the paper, we proposed a rather complicated hierarchical generative model that basically had a kind of base layer where the agent is just performing this focused attention task, a superordinate layer of hidden mental states, which essentially represent what the agent is focused on, where the agent's attentional state is being focused, and then states of what you might call meta-awareness, which are to attentional states what attentional states are to cognitive states. So basically, it is attending where you are attending. And with this kind of setup, we were able to not only make sense of this cycle of focused attention, but we simulated it, and I think gained some insight into the processes of focused attention. These models, note, are not at all written in terms of the underlying neural processes. This is just a characterization of the dynamics of first-person experience. So in computational phenomenology, this additional constraint that you have to tie it back to some underlying neurophysiological activity is not present. It can be, though. If we are interested in doing that, what we're doing is generating what Francisco Varela called generative passages, which is a more rigorous approach to coupling discourses than just saying, well, somehow the neural activity underlying some representation should be isomorphic to our experience of it. Rather, the idea behind generative passages is that the phenomenological register and the modeling tools that we're using should be, and in particular, the neural modeling tools that we're using should be mutually informative and kind of come into a mutually enlightening, virtuously circular embrace. So if you're interested in doing that kind of thing, then you can make hypotheses about the link between experience and the underlying neurological activity. In the version of computational phenomenology that we've presented more recently, we make a core methodological assumption, which is that we can basically formalize the doxastic positing aspect of phenomenology. So essentially the contents of phenomenological experience as a kind of a belief or inference process. So obviously you can reject that as an interesting modeling hypothesis, But in this context, under the assumption that you can model the contents of phenomenological experience as a process of inference, then you can do all sorts of cool additional things. In particular, the active inference framework, based on this new physics of information, Bayesian mechanics, tells you something about the energy requirements and information flow that must be in place for beliefs to change over time. So here you have a kind of mutual circulation between phenomenological descriptions and a way to model the time evolution of contents, phenomenological contents. So yeah, and this is one proposal to kind of link up these different discourses together. I guess the important thing is that this is an optional step. It's possible to just conduct your computational phenomenology entirely within the first-person phenomenological domain. But the descriptions that you produce in this way constrain possible biological explanations of the same in interesting ways. So that's it. That's all I wanted to say today. I just wanted to present computational phenomenology at a high level. And yeah, I suppose we have a good amount of time for questions and such.